Okay, so I stated this theorem before, so I recorded here, and maybe at the end of this session, I will discuss a bit about the proof of this. But this is a result which I stated last time as a motivation of discussing ancient solutions. So today what I'm going to do is first I want to draw the consequences from what we did last time. And then with the help of this proposition, I mean this is a crucial result, and we can have a corresponding structure results on the Ricci flow. Okay, on the Ricci flow. So then tomorrow we will do a surgery. Okay. So remember I guess I remind you what we did last time. I mean last Thursday, and so we discussed this ancient solution. We talked about so we talked about asymptotic shrinking soliton, and we prove the existence of asymptotic shrinking soliton. So basically we did the following. So let's see. So we have a suppose. So we from now suppose first. Okay, maybe we ignore this for a while. Just so suppose n and g is shrinking is ancient kappa solution. Kappa is some positive constant. Okay, so this is defined at okay. So last time I said if you take for any sigma k, for any tau, okay, tau is minus t. Okay, so for any tau there is a q tau in the n, such that this air, the distance function from some given point. So given point is given by p. I just remind you what the sum I did before of q tau, and the tau is a minimum. Is of air x of tau. Okay, x tau on n. So then what we did is we look at the g tau, okay, g tau of t. I look at this Ricci flow, and it's defined as this of tau of t. Okay. Let me see, it's which way around. So. So we defined this, and then we look at asymptotically, and yeah. So then we know this is by taking a subsequence. This is basically converged to asymptotically as tau goes to 0 in the subsequence in a asymptotically shrinking soliton. Ricci soliton. So now, why did we study this? The reason is now so then we proved that there are two. This soliton, there are two possibilities. One is case one is So then case one, we say this is the shrinking soliton here. Let's see, make it g infinity. Say g infinity. Okay, so either m, so maybe on the m infinity, g infinity. I mean, this may not be same as the original manifold. So first case is m infinity is compact. So then I said before, then this is very easy. So then the m infinity is simply S3 quotient by thing. Okay, and G infinity this time is a round metric. So round metric means it's a standard metric on S3 and descended to this quotient. So of course this time the volume of this is S3 quotient this. Of course it's a volume of S3, which is a fixed number because of we normalize this to be a scalar curve to be 1. So divide by the order of group. Okay, so this is basically your kappa. Okay, so this is basically your kappa. So the large the group is, this is a finite group. The larger the group is, the smaller kappa is. So maybe I should say things is I say I fix a kappa here. So I discussed the ancient solutions, but and we proved so there's always a kappa depending on finite time. Okay, depending on the time, so that this Ricci flow is kappa long collapsed. But this kappa so far has no a priori bound. So kappa could be any positive constant. For example, here, if you start from manifold with large group here, then kappa is very small. Okay, so that's the best you can do if I just look at this case. But the good things here, this is very rigid. For ancient solutions, if in this case we imply, if this case I said this actually imply mgt, this time is actually it's not moved, it's just S3. And this is S3 with a round metric. Okay. So even though here the kappa could be made as small as possible as I showed here, but this time the ancient solution are rather rigid, right? They are just the standard flow and standard metric. Standard space and standard metric. So other case we rule out is other case we say is okay, if M infinity is non-compact. So then last time I proved first it's so there's no positive shrinking soliton. So the shrinking soliton has to split a line factor. So that this time the M infinity, G infinity is also standard. It's just the S2 cross R with a standard metric, standard flow. Maybe I just put a standard here. Or S2 cross this, divide by this Z2 action, and with standard flow. Okay. So standard flow means is a trivial metric. It's just a product metric here. And on this factor, it's a standard round flow. And here is just a constant. It's just a flat. It's just standard things on lines. Okay. So this is Z2 action just is antipolar. It's on this factor antipolar map. Here it's just a change of sign here. Okay. So that's good. So it's also very standard. So then what we can conclude is the following in this case. So which I will give you a proof of this. It's a very simple factor. So this time there is a kappa 0. It's universal kappa 0. So I'm talking about three-dimensional case here, okay? Because because this here I use 3 dimension, okay? Or even though here I don't quite use the dimension here. So here. So there's a kappa 0 which is uniform, such that mgt is kappa 0 long collapsed. Okay, so this is an improvement, refinement, because at the beginning I just assume is kappa solution for any kappa. This kappa could be much smaller than this kappa 0 here. So on the other hand, if it's non-compact, if a shrinking soliton is non-compact, you have a uniform kappa 0 here. That's crucial. So now let's see how why this is true. So first, let me make a proof. Is very simple. First, we just look at we know there is a sequence. Tau k goes to 0. Okay, goes to infinity, such that sigma k, which is defined to be a sigma tau k, converge to a shrinking solid. This is by assumption, okay? A non-compact shrinking solid. I mean, if it's one sequence converge to non-compact shrinking solid, of course, every sequence does that because this is mutually exclude each other. Okay, so this non-compact shrinking soliton. Okay, and which is of this type. Okay, so this convergence means you actually, I should say, this is more strictly speaking, you should have a space. So I should say it's such that, maybe I make it such that M, and then this metric, and then there is also QK equal to a Q tau K, the base point. Okay. So, and this converge to the Q infinity here. Okay. So now, if I look at this K function here, okay. So the K function, say this is a distance function, reduced distance function. So recall this is a reduced distance function. Reduce the length from x p0 in M. So this is given at the beginning. Okay, it's arbitrary, but it's given. Okay, and with respect to the changing metric. Okay. So then we know this is a scaling invariant. So we know then this is scaling invariant. So this K of Q, okay, at point sigma tau, sorry, is let me record this. So this should be equal to maybe I just do this now. So this is equal to original x. This is original reduced. This means the original reduced length function of this flow here of Q and the tau K time. Okay. So this you can check directly by using definitions, right? Because you have different factors in the. I mean, you define this in terms of air geodesics, and this is just a length of air minimizing air geodesics, and you can just look at. Okay, so this is this things here is reduced volume K, the corresponding reduced volume of this tau is this implies. So this is reduced volume of GK here, and it's just the reduced volume of. So this is reduced volume of. Let me write it because so reduce the volume for GK. So this is just a reduced volume from X to this. Okay, so now let me draw the picture. So this is a fixed. This is reduced volume for fixed metric. So now, if when the K is sufficiently big, so this is K sufficiently big. So what we have is this. If you look at, I just draw the map here. So MGK of maybe I put this way. So if I look at the unit ball, okay, with respect to GK metric, so this is at QK of so maybe I put the GK metric here, okay, and at the time maybe say giving time tau, okay, so maybe a time equal to 1, okay, so it's tau equal to 1 or t equal to -1, so this is corresponding t, and then you look at the unit size, okay. So this goes to this corresponding part of this. So this is close to the corresponding part in the standard solution. This is the standard solution in S2 cross R or S2 cross R quotient by Z2. Okay, so that means okay, so okay, so that implies this thing here, okay. So the LK, so LK say if a Q of a tau, which is less equal to some corresponding the length of corresponding air geodesics of a K of how do I say? So let's say let this okay. So let the tau say big equal to 1. Okay. So then let's say let the air so let the gamma be a geodesic, be a curve from x P0 to a Q of tau, okay, such that the first gamma is made of two parts. It's joined gamma 1 and then gamma 2. So gamma 1 is from 0 to K. Okay. So 0 to 1 is the reparametrization of goes to M. Is the reparametrization, and how do I say? It's a scaling or reparametrization of a curve, the air geodesic, from x to a qk in a interval of 0 to tau k. Okay. So with respect to origin metric, if tau k in the new metric, it means 1 here. Okay. So then gamma 2 is simply from 1 and the tau from to m, joining qk to q. Okay. So gamma 2 is also air geodesic. See. So that implies because length of this, so that implies the air k of tau this is always less equal to LK of QK and 1. Okay, so QK and 1, and plus the length of this. Okay. So now the first one I already know this is just Lx of QK by scaling of tau k. So this is nothing else but just less equal to 3 over 2. Okay. And now, if I take, for example, I take a tau to be a 1.1 or something like that. So I just suppose the Q is inside here. Okay. So then this will be bounded. See, let's just say bounded if a Q is in a B1, B of this ball here, BK this ball here. Okay. Because this one is sufficiently close to the standard one, you just use the things in the standard thing to compute it. Okay, let's assume tau is, so we can take this to be 2, for example. I don't really need the, so just fix some tau big equal to 0. Okay. Okay, so that implies this is this maybe depends on constant, depends on tau, but a tau will be fixed. Okay. So the things here, this is uniform. It's uniform in K. Uniform in K. So with this, you will be able to prove because volume of this is fixed. It's just close to some corresponding ball here. So that implies the reduced volume. Say you fix tau to be 2, for example. So this tau. So let's say tau is 2 here. Okay. Oh. So it's a bigger equal to a. So it's bigger equal to some fixed constant, say kappa. Here. Or maybe some fixed constant prime. Okay. So that will imply, so if you back to this is equal to say the tau k, tau x of reduced volume of 2k is bigger to kappa 0 prime. But since the tau k goes to infinity by monotonicity, all this is maybe I should fix some. Let's fix some here to distinguish it. Okay, sorry for. Okay. So then for any tau, this is bigger equal to kappa 0. Okay, for any tau. Because for any tau, I can always find some tau k such that this is smaller than twice of tau k, and then by the monotonicity, the bigger the tau k is, the smaller reduced volume is. Okay, so then I have this. So for ancient kappa solution, as long as the shrinking soliton, asymptotic shrinking solid is non-compact, I have a uniform low bound for this reduced volume from any point x. So then by arguments we had before, long argument on the reduced, then by the same repeat argument, by the same argument improving long collapsing, we know that this volume, so there is kappa 0, which may depend on this prime here, such that the volume is of x. So it's such that this is kappa 0 long collapse. So I have this uniform bound on low bound on the reducing. So here I'm not going to repeat the argument. I use this. Okay. So then what good of this? The good of this is the following compact theorem, which I have no time to prove it now. But then we have a theorem. You can either look at the book or this is in the first paper. So called 11.7. Okay. So the theorem says the following. Now, it's actually compactness of ancient solutions. So the set of all ancient kappa 0 kappa solutions for fixed chi, okay? Or it's maybe I just say kappa 0. Let's see, for kappa 0 for let's see any fixed kappa okay. So it's compact modular scaling. So that is more precise. Okay, so I should say 3-dimensional. Okay, it's so I mean, this somehow has nothing to do with that. It's an independent theorem, but combining with that, we have nice consequences, as I'm going to state next. So that is from any sequence of ancient such solutions with say m alpha, g alpha, and x alpha. See, okay. Zero. Addition of r of p alpha of 0 equal to 1. Okay. So with alpha here means a scalar curvature of corresponding g alpha. Okay. So has a convergent subsequence. So from here we can extract convergent subsequence, a smooth convergent subsequence. And the limit so say m infinity, g infinity, and x infinity belong to the same class. Same class. So of course the m infinity here so m infinity may have a different topology. So manifold may change limit, but it's same class. So same class means the same of kappa ancient and kappa solutions. So in fact, for example, might have a compact ancient solutions, and the limit is non-compact. So you have to be careful. Here I say it's I might have a compact ancient solution which are not standard here, because asymptotic solidity may be non-compact. Okay. So here I say it's a standard if asymptotic solidity is compact. So that's two different things. Okay. So this does not rule out the possibility of this being compact. Okay. It's only rule out the possibility. It's only take care of those cases where the asymptotic solidity are compact. Okay. So as an example, I just say this might be compact, but in the limit may be non-compact. Okay. But this compactness theorem says has a immediate consequence. The corollary, I will state a few consequences, but let me first state the one corollary is the following. For any so they are uniform constant, eta, such that for any, let me state in the right way. So this is can only depend on dimension. So maybe I will emphasize this universal constant. So such that for at each point of any ancient kappa solution, okay, we have the estimate. So this is kind of regularity estimate. So we have estimate is gradient R of less equal to eta of R, the time derivative of R square here. So these exponents are natural because just make it a scaling invariant. Okay, so these both sides have the same scaling, because you have got to be scaling invariant, because ancient solution you can always scale them. Okay, scale. So this estimate shouldn't be, this constant shouldn't depend on scaling constant. Okay. So here for any kappa. So why this is true? We have first, in this case, it's true, doesn't matter what the group is, because this is a standard metric. You compute both sides. I mean, you can write down the flow. Okay? I mean, of course, gradient R is 0 in this case. There's nothing to estimate. But RT is fixed. Okay. So anyway, this case you can check directly. But this case, you have a universal kappa 0, then you have a compactness here. Okay. Then the kappa is fixed. So in the second case, kappa is fixed. So then you apply compactness there. So if this is not true, you take a sequence. So this is violated. Then you take a limit, you get contradiction. That's it. Okay. But this is a uniform estimate. So it's not, it'd be nice to have an estimate without doing this way. This is more like proving estimate by using kind of Liouville type arguments. Okay, to prove something. It'd be nice to have a more direct proof of it. Okay. So this is maybe I just say that. So this estimate will pass to any Ricci flow when the curvature is sufficiently big, right? So here, so this theorem. So now you see why we need to study ancient solution now. So with this theorem here, I know there is R0, which may depend on something a priori constant, such that if a curvature is sufficiently big, satisfy this condition, then I know the corresponding part, the part the neighborhood of this flow is close to some ancient solution. So then you will also satisfy that estimate there. Okay. So this estimate is also true for any Ricci flow, where for the part of Ricci flow where the curvature is sufficiently big. Okay. So next, let me draw some further conclusions, which I maybe just give explain a little bit, not quite prove this. So furthermore, we have the following things. So then we limit. So next time I will not state it. So furthermore, we have the following things. So it's a little bit complicated to describe, but it's okay. So moreover, for sufficient small epsilon, but it's small epsilon is just like in this epsilon like a certain stability. Right? So it's also universal, can be made universal, okay, uniform. So they are constant. two constants. These two constants depends on epsilon. Okay. So such that the following is true. So this again is still in the ancient solution. So for any xt in an ancient solution, kappa solution, G. Okay. So there is R certified and radius R, and this is less equal to C1 of scalar curvature inverse a half. Okay. So it's modular scaling factor. Okay. So and the neighborhood of B, and B is contained in the xt of R and twice of a ball. So it's contained a ball of radius R, and it's contained in the ball of radius 2R. So it's a region with has a comparable size with a geodesic sphere, a geodesic ball, which is of the following type. Okay. So first, A, maybe I remind you later. So B is a strong epsilon neck. Maybe I will do after I state it. Okay, and the B is a so-called epsilon cap. And that's 4 cases. 3 is B is closed, and the diffeomorphic to S3 or RP3. So D. So B is a standard, B is closed. So B is just same as, maybe I just write this as a, so this time not only means the topological same, it's isometrically same. Okay. So here I say this means isometrically same. Okay. So there are 4 cases, and also you haven't seen a C2 here. So C2 here is the scalar curvature is also has a condition in the T, so I running out of space. So maybe I put it here. So now I haven't used a C2 yet. So maybe let me just so scalar curvature in B is between okay. So dB y t is between C over say dx t. Okay, because scalar curve is positive in this case. So okay, between a C2 and the C2 inverse. Okay. And you also have some volume things. So maybe I say volume in the first three cases. You also volume of B is bigger or equal to C2 inverse of Rxt in A to C case. Of course, this case you cannot because gamma can be very big. Okay. So let's just this is a further. So this part is a further. So this whole corollary, I will say is make a name here. So this let's see if I say if these things are satisfied, I would say so maybe I state over here. So this property is stated in a remark, maybe. The properties in the last corollary, is called, let's say, let's refer to as so the canonical neighborhood assumption. So when I say a region satisfies a canonical neighborhood assumption, or a solution satisfies neighborhood assumption, if at every point you have those properties. If I say certain region satisfies that means any point in that region will have that properties. So we have such a neighborhood with these descriptions, and we have this estimate here. So now, what is those things over here? Okay, so I guess Louis, you mentioned that you said something about epsilon lag, right? So maybe I just give you a definition. So it's rather okay. So now let's make a few definitions so that okay. So this is one remark, and second, so maybe I just so what is epsilon lag? Okay. So I say the ball is so a region is epsilon lag if after scaling. Let's put it this way. So I see so it's called epsilon lag. if after scaling, so namely you normalize curvature, scalar curvature to one point to be 1, okay, after scaling, okay, then it is epsilon close to standard. Standard metric on a cross I. Okay, so maybe I put it this way. So cross minus epsilon inverse maybe I erase this so we have some time to. Okay, and the epsilon close, like this here, epsilon close means in a Cn topology with for n bigger than. Okay. So that means you have a diffeomorphism from this space to that space, such that if you pull back this metric or push this metric to that things, and then the difference is a tensor is measured with respect to the standard metric here is in the Cn topology is small is less than epsilon. Okay, so it's a strong epsilon lag. If a corresponding parabolic neighborhood. So this is a P of so that means the B cross this okay, of 0, let me see, it's open or closed, minus R0 of, so depends on T, so T minus, okay, is epsilon close to the lag. Standard solution. Ricci flow solution on a S2 minus cross. So this is a space, and then cross the time interval. That's from 1 to 0. Okay. Maybe here I should say the regional concept. I look at the scalar curvature here. So scalar curvature at x t we start with. After scaling, again, it's after scaling. So here I include the scaling factor here. Okay. So if I drop curvature, that means after scaling I did that. So this is a strong epsilon lag, and So then you have a metric on the ball of if maybe I draw the picture now. So if your region after scanning looks like this, so there are some parts you don't know. So then the outside compact region, if this is a epsilon cap, that means outside compact region is the epsilon lab. So this part is epsilon lab. And closed by some compact region, okay, of a fixed size, a comparable size. The size is also comparable with the curvature here. So then this is called the epsilon cap. Epsilon cap. Okay. So you can extend. So you can further take. So this is always has a fixed size here, and you can further see a so-called epsilon tube. So I just draw a picture now. So epsilon tube is like this. So that means you can cut this into a part, such that each of these is epsilon lambda. Okay. Okay. You can cut this into a part, such that each part is a strong epsilon lambda. And also is epsilon lambda, and also curvature stay bounded. And the curvature stay bounded. So you have a set, maybe very, very long. It's maybe much longer than this interval here, but you can always cut. It's made of this. You can divide them into such epsilon lambda, such that okay. But the point is the curvature stay bounded. You can also say epsilon home. Basically, it's also like this. You can cut them into epsilon lambda, but on the other hand, curvature may not be bounded. Okay, so such that, so of course this goes slowly. I should, this is too so slowly to things. Okay, and the curvature is unbounded at one end. So I use it because next time I need to. When I do a surgery, I need this. So such that each part, so this size of 2 epsilon inverse, each of these is still epsilon lambda. But this scaling factor, when I say epsilon lambda, it's always up to a certain scaling. Okay, when I normalize, it becomes a standard one. So remember that. But each time, each of these epsilon lambda I can scale down. If the scale factor goes to infinity at the end, then that means it's a home. You could also have a double. Home, so that means both sides are unbounded. Each of these is still epsilon lambda. But the building block are always epsilon lambdas. Okay, building block are epsilon lambdas. But epsilon lambda means you have a fixed, definite size. But in the long range, it could have a different geometries depending on boundedness of curvature. Okay. Of course, you can also say so one side is capped. So it's capped. So it's like, so this. So that means outside the compact set, so this part is a fixed size compact set, you don't know, it's not necessarily epsilon lambda, then you become like epsilon lambda. Epsilon lambda, okay. You could cap on both sides, so then you will give you this possibility here. So the good thing is you can only cap 2 ends. You cannot have more than more than 2 ends. Okay. So the reason for that is splitting there. Okay, splitting there, because if you have 2 ends, so if you have a space, if this is 2 ends are sufficiently far from each other, then in the middle has to be epsilon lag because of splitting things. Okay, splitting. Why? Because you can think. So I always think those just bear in the mind all these things. You are talking about region where the curvature is very, very big. Okay, and if these 2 ends are sufficiently apart from each other after curvature scaling, this is very, very far. So at point here, there will be like a line segment, sufficiently long line segment. So if you have a whole line, that means you have to split because curvature is non-negative. Okay. So then you reduce to S2 cross R or S2 cross R quotient by Z2. Okay. So that's why you have you cannot have 3 ends, 3 caps, because that's where Y-net scanning, Y-net splitting things. So basically proof here, I mean, indeed, this is immediately follows from what I said, but here you need to run some further arguments of compactness, because it does not directly from those things I stated. So of course you know you have a region with a fixed type of topology. The topology is compact size, okay? But to specify these are only types, you have to run a compact argument. Say, suppose you don't have such a constant, you will have a sequence of things, such that this is none of this is satisfied. Okay, so you then run the limit. In the limit, you will get again. You try to use splitting and analyze. Either you get in the limit you get the space of positive curvature. So in that case, it has to be R3. Okay, so you get part of that is S3 topological type. If it's not positive, strictly positive curve, then split as a cylinder. So then you have epsilon lag appeals. So of course, I didn't mean to give you a proof here. It's a little bit tedious to do that, but it's basically runs through repeat arguments. So to prove it by contradictions. So if it's not true, you take a sequence, then you argue in the limit, examine what the limit is. Okay. And this is easy to derive. This follows from compactness. Why? Because if this doesn't hold, you take sequence ancient solutions, you take subsequent is compact, of course this will be true in the limit. Okay. This is easy. And here you need a little bit of geometry involved. Arguments. Okay. So those give you a classification of structure of ancient solutions locally, and because of that, the compactness theorem, this also hold for a region where the curvature is sufficiently big. Take it? So here, this is for ancient solutions, right? But ancient solution, the part of region where the curvature is very big for giving Ricci flow is close to a corresponding part of ancient solutions. So that will tell you this. That will imply this region also is of that type. So for Ricci flow, when the curvature is sufficiently big, it satisfies so-called canonical Leopold assumptions that those properties stay there. Okay. So you can imagine this is important, because I said the whole issue last week. I said whole issue is to deal with the singularities. The singularity is where the curvature is sufficiently big, and now I have an understanding of that. At least locally, each part have a geometry understanding. Okay. So maybe any questions before I is that get some ideas or?
So this is all singularities at this time?
All singularity at this time, yes. So RP3 is more like you have, for example, you have a asymptotic soliton is a shrinking soliton is quotient by Z2, which is RP3 minus ball. Right. So okay. So let me see what to do. I can either let me maybe then let me outline a proof of that if you have no objection. So let me outline a proof of these things. Okay. I think I. So proof of this thing here. Okay, so this is you can either and so this in the first paper is 12.1 in the first paper. And also reference, you can look at my book with also I think it's this Kleiner knot. Okay. So how we basically prove following the original sketched argument, and in the actual original statement, even in the statement I gave you last time, I forgot to put a bar here. Okay, so RZ or the original statement of Perma was actually wrong. Not wrong means not sufficient. Okay, so not sufficient for proof. It's maybe just a typo, which was found out by actually graduate student at Wisconsin. So let me give a proof of this. So we prove it by contradiction. So it's not it's actually I guess Hamilton probably still try to give a proof of this more directly. So let's say so we prove by contradiction. Okay. So suppose it's not true. Suppose we have a sequence. So epsilon is fixed, but it's small. Okay. We probably in the course of proof we choose epsilon, but let's say epsilon is small. So suppose we have a sequence of a k. The things is running out of notations. So suppose I have a sequence of a Ricci flow. Okay, for t less equal to capital T. And Rk goes to 0. And all this satisfy these conditions, and all satisfy these conditions, and such that and xk, tk, okay, with tk. I mean, this is not important, just normalizing factor. You can make it less equal to, bigger equal to half. That's just not too close to 0. And qk, so this is a scalar coefficient gk. But on the other hand, this is not close to. Okay, so let's plot this region as say is corresponding, and maybe the D for the corresponding region D for this metric G of xt. Give a name for that. So let's see, this region is not close to. So for this gk, maybe I put k down here. So of xk, tk, this region is not close to any ancient solution. So want to get the contradiction, namely I want to take a subsequence. I can try to extract the subsequence so that in the limit I get ancient solutions. Okay. So first step, what you do is you want to rechoose this xk, rk. So you want to rechoose xk, ik, tk, tk. In a sense, this is the worst things, worst point which those conditions are violated. Okay. So more precisely, this is giving as follows: is so I want to say I want to rechoose this such that okay. Such that you have following conditions. So, such that this, how do I say, and this canonical neighborhood assumption. So let's see. So I want to see it's these conclusions in the corollary. Fails for and holds for any yt, okay, inside of mk. Mk is the space of corresponding space of this. Okay. And we cross with tk hk of qk inverse. Okay. And for any for which RYT is twice than QK. So namely, I want to choose this is a worst point. That if points are if a scalar curvature bigger, twice bigger than this constant, then it's close to a canonical neighborhood. Okay, so basically, what I only need is that the curvature bound these things here. So I will use only in the proof use only this. Okay. So on the other hand, I can also choose the HK where the HK goes to infinity. So I need this to be sufficient now. So this is easy to prove. Basically, if this is not true, if for xk, tk is not true, then you can choose a new yk, tk prime such that it's not close to ancient solutions. So now you replace that and look at the corresponding region. So because your qk increased by twice, and the region you look at here is also contained this time interval here. Okay. So you keep doing. Each time you shrink the size by half. You can only do finite many times, right? Because for each fixed k, I don't control number of times you need to do, but you can only do finite many times for each k. So eventually, because if a sufficient is small, if each time you cut by half, you cut the time interval by half, because eventually we'll go to some smooth solutions. So it got to be true. So this is you need to do by the standard argument. Okay. Each time it's not true, you pick up number and you shrink the size by half, then you do it again. Okay. So eventually you can do it. So once this is done, then this is done, then you know you have that estimate. So you say you have this estimate. So then we have an estimate star for any yt for which ryt is bigger than 2. So in particular, that implies, maybe I just state, let me still. So that implies the curvature will be bounded in a small region. So that implies there is a small constant depending on your kappa, okay, such that it's small, such that this rxt is less equal to. So this is so when it's sufficiently big, this scalar curve is always non-negative. So this is 4 times of a qk. Okay, so this is for gk. Okay. So let's drop the k law. Assume this is a k here. So this is a q for qk. Okay. So we fix each k. We do that. Okay. We do that. So this is for any xt, for any x of distance, so xk. So of tk. So maybe let's put it in a notation now. So let's equal to c of a q of maybe put this way. Okay. So I put everything put by here. So plot bar here. Okay, so maybe I even drop this plot bar here. So it's T bar. So this is less equal Q bar inverse half. Okay, and how do I say there's some conventions. It's not anyway. It's not completely proof. It doesn't really matter because there's slight difference here. So this is this, and also time is. Okay. So where I will fix the T bar as a TK, just drop the K, and the X bar is XK. So for convenience, I make Q bar to be a QK plus. Okay. So that I don't need to write XK K at every time. But you just bear in mind we are doing this limiting argument. So actually there is a limiting involved here. So why is this true? Because this is because of this. Because this. Okay. So if you don't travel if a point does not travel too long, and you have this then you have this I don't know if I want to plot this GK. Maybe I plot GK. So if your points are not too far from this base point, maybe I still go back to K here. I'm sorry. So it's K X K. Maybe then I drop this. But I need to take a limit next. It's a little bit tricky to do that without K. Okay. So we have this region. So now then what you can do is you can take you can define a rescaled metric. You define a say G bar K of X T to be you scale it to be a QK of G K and X QK of T. Okay, QK inverse of T. Okay. So then you want to take a limit, and you hopefully in the limit you get ancient solution too. And this solution, so then this sigma K, the curvature of sigma K bar at point XK, TK, okay, and maybe I switch it to a, so I plot this to be a TK. Okay, so then this is 0. Okay, so T is less equal to 0. Okay, so then this is identical to 1. Okay. So okay, so and also it's and G K of bar of YT is less equal to 4. Okay, and it's bounded from above because this is a region where the scalar curvature is very, very big. By this pinching condition, we know the scalar curvature is positive when the scalar curvature is sufficiently, or when the curvature is sufficiently big. So this is bounded. It's bounded from above in the region. After scaling, this is in the region of xt of a distance d t distance t0. So it's in terms of gk bar of xk less equal to c and tk. Sorry, c less equal to t less equal to 0. Okay, so I switch. So it's bounded here. So if you look at the, so maybe I put this way. Okay, so this is your manifold, MK. This is your time. Okay, and I fix the XK. So after scanning, this is the XK0. So this is a picture for GK bar. Okay. And I know this small region here is bounded. Okay. So then by compactness, once you have a bounded curvature, and you know it's a non-collapse, okay, by complex theorem, once the curvature is bounded, and you also have condition on non-collapsing, so namely volume is not too small. So then you know the flow GK T will converge, and with this reference converge to something. So this is on the. So we are converge to there. But M infinity here, I should put the M infinity 0 here. It may not be complete. Could be only a bounded region. So this only I should say it's not sorry. So the only thing is this bounded only in the part where the region and the curvature are bounded. So in the part region where the curvature of GK bar are uniform bounded. Okay, independent of T. Okay, so X T depends on X. Okay. So only in the region, because you need the curvature bound in order to have a compactness. So in the limit, this space may not be complete. Okay, so you made it complete. Namely, if you're traveling along the curvature, if you take some point here, okay, and this only have a finite distance, uniform bounded distance. See, this is a zk here, and with a bounded distance, bounded distance, but the curvature of a zk of maybe the 0 of gk bar could go to infinity. So you have to rule out this in order to get a complete space. So the things, the clamp, Lex clamp, this is one of key clamp. So they call it clamp 2. Now suppose the choice first is clamp 1. So it's a clamp there is a bound C depends on a distance of such that the depends on distance C. Okay, such that the curvature of GK bar of X0 is uniformly bounded by C. This is a C depends on this distance D. Say maybe I put it this way. D for any X for any X dx xk bar, which measures in terms of gk bar, is bounded by D. Okay. So first statement you do this. So you prove this claim. So let me say why this is why this might be true. The reason is if you have a say I draw a picture here. So if you have a reference point here, And if you have some point finite distance, and say the yk of 0, okay, so you join them by geodesic. So you pick up some zk. Okay, and suppose yk. So distance of yk and xk is uniform bounded by some constant. Okay, constant d. Sorry. Okay, and on this part, this is a gamma k in the geodesic. So the curvature of say x0 is always bigger than 2qk for any x, maybe for any x in a gamma between z and y. Okay. Okay. And you also want this yk. So suppose have this say this yk 0 goes to infinity. So suppose you have this. Okay, maybe I say. So if this is claim is not true, you can pick up the sequence. Then because you already have a canonical neighborhood assumption here, when curvature is sufficiently big, so twice big. So then all this part have a epsilon neighborhood. So it's actually epsilon tube. So and the size of epsilon tube gets smaller and smaller because scalar curvature goes up. So in the limit here. So in the limit, this m infinity, okay, of 0 of g bar, okay, looks like a cone. Cone with a vortex. Vortex at the limit of yk. So namely, when this picture comes in, this is in this. If you look at the manifold, this is near along this geodesic here. At each point, there's a small epsilon neighborhood. There's a small neighborhood which is epsilon neck, and this neck is shrinking and shrinking. And in the limit, this is also curvature of this is non-negative. So, but this is not possible because of maximum principle. Why? Because it looks like a cone, so eventually you can, by doing a kind of you do a kind again, do another set of limiting arguments, you will get a limiting Ricci flow on the cone, on the tangent cone, on the cone, okay, which is not possible because cone has a vanishing directions. It has to split, okay. But on the other hand, the cone does not split directly. So why you have a limit tangent cone because the curvature is non-negative. So you know it's for space with non-negative curvature. You have a comparison. You have the distance that is decreasing along. How do I say? So use the modularity of distance functions. You can establish. You can extract a sequence, subsequence, such which converge to a Ricci flow on the cone, tangent cone, by after certain scannings. So that will give you a contradiction. The contradiction comes out because you assume this curvature blows up at a finite distance. Okay. So I guess it's hard for me to do it here. So anyway, so the key point here is if there is if a curvature blows up at a finite distance, then you will be able to blow up in the appropriate way, scaling up in the appropriate way, such that you will get a Ricci flow on the cone. metric cone, and with non-negative sectional curvature. But Ricci flow on the cone is not possible because it's wireless maximum principle argument. Maximum principle says for Ricci flow. So here I use the Ricci flow. Of course, you have a metric on the cone, but it's because I have to remember here we come from Ricci flow. You cannot, the Ricci flow does not match with cone structures. Does not preserve cone structures. Okay, because maximum principle. Okay, so this tell you you can actually bound the curvature at any finite distance, but this bound may depend on distance. So actually, I already said more than what the Paramount said. Even I only probably because he only said one sentence basically. So anyway, so we bound. So this step, by this claim, we can bound the curvature at any finite distance. Then you have this. So you can bound the curvature at a certain back up time a little bit because time derivative is bounded. So you can have a certain region like this. So this size length of this time interval depends on a curvature at this point. How far you can travel back depends on curvature at this point. Okay. So then you get some region like this. So on that is your limiting flow. Okay. It's not rich in the prior, so I can drop this now. It's a complete space. M bar is complete space, and your flow can go back to a certain interval, and this certain interval may depend on point. So next thing you do, using this fact, you prove curvature is actually bounded on the time interval. Okay, so maybe I stated it here. So now, so we have so by this claim, we know there is a region. So there's a region called xt contained in M infinity across a time interval. See, and t is less than t. So M infinity is complete now. So by claim M infinity is complete. Okay. So maybe I do it later. Sorry. So this t less than tk less than some constant. How do I say? It's a function of things. Function of infinity, it's a g infinity bar, and less equal to t, less equal to 0. Okay, so there's this, and so such that g bar is a flow. On it. Okay, and moreover, this curvature of this G infinity bar is bigger to 0 and is complete on the M0 is complete. Okay, but this function is a function of depend on distance goes to 0 as distance goes to infinity. So then what next I claim is this part is already used supposed to be in the previous step in the proving a compactness of ancient kappa solution, which I didn't do. So in fact, the curvature of G bar is uniform bounded on M infinity. So once this is uniform, so there's a corner Ricci, and this function. Now it's a so then we can take function, take f big equal to some fixed constant. So that constant depends on that estimate over there. So this depends. Because if it's uniform bounded, then in the sequence, this is also uniform bounded all the way. So the reason for this true is because if this is not true, if you have a sequence of points where you have sequence of points goes to infinity where the curvature blows up, and again near those points, because I have a canonical neighborhood assumption, near each of these points there's an epsilon neck. So namely you have a sequence of epsilon neck. Size of epsilon neck goes to 0. Okay. In the manifold of positive non-negative curvature, that's not possible. You can use the Boltzmann function to get a contradiction. Okay. So that's used some this structural theorem for manifolds non-negative curvature, and the strong fact that exists on epsilon neck. Okay, when the curvature is sufficiently big. So then what I do is so I guess I need to stop now. Actually, last step is also interesting. So by this claim, we can take this to be true. So then we know the Ricci flow is so then what we know, this G infinity bar exists as a flow on M infinity cross some minus T prime 0. So only thing I need is so next I need to prove to show T. But this is a sequence of GK bar, because GK bar we are close to ancient solution. If this is true, if this is true, why? Because if this is true, then this is ancient solution, kappa ancient solution. And we assume, so then the GK, a k sufficiently big, is close to this part. But I know GK does not close to ancient solution, near the base point. So that's contradiction. So only thing I need to prove, I say I can extend this T prime. So how do I do that? So I want to say a curvature will stay uniform bounded if T prime is finite. So that's a key point to prove, right? Because if a curvature is uniform bounded at T prime, on the interval, then you can using that assumption again, you can extend across this point. Okay. So the key issue here, key point to prove if T prime is finite, prove then the curvature of G infinity bar is bounded, depend on T prime. So that will imply GK bar are uniform bounded for in an interval for k sufficiently big. So that means you can, because by this, by star, GK will be uniformly bounded by some maybe twice of this on minus T epsilon plus some delta of plus some this small c, I guess. Maybe I put 4 times here. It doesn't matter. So that means T prime is not a maximum interval the flow exists. Okay, so in order to do this, in order to bound this, in order to do this, we need to use the, first we use the Halak type inequality to prove there are certain curvature bound. Then use the structural theorem for manifolds with non-positive or non-negative curvature. Okay. And I think I stop here. It's certainly it's a very sketchy proof, but in the time stream, I'm sorry. So if you are interested, we can discuss more behind the class. Thank you.